third part of this chapter, exponential modelling. So we can use exponential function to model a real world problem, such as population growth, and we're going to look at example 5. Okay, so this says the density of pesticide in a given field is modelled by the equation P equals 160 e to the minus 0.0060. So e to the minus graph, we know it's going to be going down. So it's going to be an example of exponential decay. It's going to get smaller and smaller and smaller. So with this, you're going to dump the pesticide, and as time goes by, the density of the pesticide is going to decrease, never quite reaching zero, but getting close to it. So it says, firstly, use the model to estimate the density of the pesticide after 15 days, so T equals 15. So all we need to do is just substitute that. Should we use the calculator? So we've got 160 times e to the power of minus 0.006, and then t is 15. So we can see that's 146 rounds to 0.2 milligrams per metre square. Okay, so that's after 15 days. It says B, interpret the meaning of 160. Well, 160 is going to the value when t equals 0. Because if you put t equals 0 into here, you get e to the minus 0, e to the 0, which is 1. So P equals 160 is going to be the density when the pesticide is first applied. So the original value of the density. So P equals 160 when t equals 0. So that will be the original density. Or the initial density is probably a better way of calling that. C, work out or show that dp dt equals kp. So this means to differentiate p with respect to t. So here's p. We learnt in the last lesson how to differentiate an exponential function. We just multiply by the coefficient of the power, and then this bit stays the same. So dp dt is going to be 160 times minus 0.006 minus 0.96 e to the minus 0.006t. So it's of this form where k equals minus 0.96. Now, the fact that this value is negative means that the gradient's going to be decreasing. So it's going to be an example of exponential decay, but we know that anyway from this part of the graph. So in terms of sketching the graph, we know it starts at 160 and then gradually gets closer and closer to the t-axis. Now be careful with this one, because it's tempting to carry on the graph on this side of the p-axis, but remember that'll be negative time, so it just doesn't exist, and you are in danger of losing marks if you were to carry on the graph beyond the p-axis in the exam, so don't do it. Okay, so that is the only example on this exercise. So if you now have a go at exercise 14C on page 318.